Hi everyone. Instead of talking about inference for proportions such as confidence intervals or hypothesis testing, Chapter 22 and this unit have to do with inferences about means or averages. Just like when we were talking about proportions, we also have confidence intervals and hypothesis tests for means based on sampling distributions or a single sample. And we're going to be centered at our population mean, which is mu. So if we found the true average of the population, that value is called mu. And our standard deviation formula, unlike that square root of p hat, 1 minus p hat over n, is this. It is our standard deviation divided by the square root of n. And sigma, in this case, that standard deviation symbol, that is our population standard deviation. And if we know what that value is, we can use this formula. In a moment here, though, we very seldom actually know what that is, so I'll show you how we approximate that using standard error. So when it comes to finding a confidence interval for a population mean, we are not going to use that standard deviation formula because we typically don't know what the population standard deviation is. So instead, we settle for standard error, which we talked about before, and we just take our sample standard deviation divided by the square root of n, which is our sample size. One of the most significant differences between inferences for proportions in last unit to what we're going to be doing now for inferences for means is that we're no longer going to use the normal model. Because we don't actually have an accurate estimate of what the population standard deviation is, we can no longer use the normal model. And what we're going to see is that the shape of our new distribution, which is going to be called the t-distribution, actually changes based on what are called degrees of freedom, and degrees of freedom are directly related to your sample size. As we work more with the t-distribution, you're going to see that as your sample size increases, the shape of the t-distribution becomes more like the normal curve. But if we have a relatively small sample size, it's actually going to be pretty well spread out. So because there is more uncertainty with t-intervals or confidence intervals for a mean, you're going to expect that your margin of error is going to be slightly larger than it was for the confidence interval for proportions. And also your p-values are going to be a little bit larger when it comes to hypothesis testing. So just keep that in mind. If, for example, we found a 95% confidence interval for a proportion, then the margin of error for the corresponding 95% confidence interval for means is going to be slightly wider. So just like last unit when we talked about one proportion z intervals, we now have a one sample t interval for a population mean, where we're trying to just estimate the value of one single population mean. So when the conditions are met, we are ready to find that confidence interval, and here is our formula. We are going to take the sample mean x bar plus or minus our new test statistic, or excuse me, the new critical value. No longer z star, it's going to be t star, which is very closely related. Our sample standard deviation divided by the square root of n. And the critical value t star, like I said before, is going to depend on the number of degrees of freedom, which is really easy to find. It is just your sample size, or n, and then you subtract 1. Like I said, we're no longer going to use the normal curve for confidence intervals for means. We're going to use the t-distribution. Just like the normal curve, though, t-distributions are going to be unimodal, so they have one central mode. It's going to be symmetric and bell-shaped, just like the normal curve. And the only difference is that the width of our t-distribution is going to change depending on the degrees of freedom. If we have fewer degrees of freedom, that's going to lead to a greater spread and a greater standard deviation. In class, I'll show you guys this applet, but you're going to see that essentially as our sample size increases, we approach a more normal looking curve. Just like last unit, we do have some assumptions and conditions that need to be checked before you can actually do a test or an interval. Luckily, 2 of the 3 conditions are exactly the same as before. We first need to make sure that we have a randomly selected sample. The other one is still that 10% condition, so our sample size has to be less than 10% of our population size. our normality condition, before we had the n times p, n times 1 minus p greater than 10. For means, we now have two ways that we can check this normal condition. The first one is that if you have a sample size greater than 30, you are good to go. So pretty straightforward. In fact, we kind of hope that we're going to have a sample size greater than 30 because that makes that condition very easy. However, if your sample size is less than 30, then you have to actually create a histogram or some sort of graph to show that it comes from an approximately normal distribution. So for the nearly normal condition, there are two ways to verify that. If your sample size is greater than 30, you're good to go. Or if you are drawing from an approximately normal, non-skewed, symmetric distribution, that also satisfies that condition. So before we dive too much further into this, I just want to give you guys a reminder that when we interpret a confidence interval, after you've checked all the conditions and we get down to the C in panic, we do not want to talk about individual vehicles or all vehicles. We are talking about the mean of a population. So when you interpret your confidence interval, you always want to refer to the mean. So instead of saying 90% of all of the vehicles drive at a speed between 29.5 and 32.5 miles per hour, you want to indicate that the true population average speed or mean speed is between those two values. You also don't want to talk about an individual car. So we are 90% confident that a randomly selected vehicle will have a speed between 29.5 and 32.5 miles an hour. Again, we're talking about a population mean and not an individual value. What you do want to say when you're interpreting a confidence interval is I am or we are 90% confident that the true mean speed of all vehicles, again, we're referring to all vehicles, the population of vehicles, is between 29.5 miles an hour and 32.5 miles per hour. Again, when interpreting a confidence interval, always mention the parameter that you're trying to estimate. A quick note on that normality condition, we have the random sample and the 10% condition. When it comes to that normality assumption, it might seem kind of daunting that you have to make some sort of graph in order to check that condition if your sample size is under 30. However, we're going to see that you can actually plug the numbers into your calculator and verify that you do have a normal curve. One other thing is that oftentimes if you're taking a test or the AP exam, they will actually provide you with a curve or with a distribution of your data. And you just have to make note of whether or not it is symmetric, not too skewed, that it's unimodal, and at least approximately normal looking. So our corresponding hypothesis test for a single population mean is called a one sample t test. Instead of a one sample t interval, now we're talking about that corresponding hypothesis test. Good news is that the conditions for a one sample t test are exactly the same as what we saw for a one sample t interval. So there's no additional conditions, there's no slight changes in our conditions. They are exactly the same as what we just went over. And what we do in our hypothesis is we, in our null, always claim that the mean is equal to something, and then we just want to go from there and say, is it less than, greater than, or not equal to? And then just be aware that when you get to the step of plugging this stuff into your calculator, you will have to define how many degrees of freedom there are. It'll ask for df, and df, again, that is just your sample size minus 1. So that is the number that you'd want to plug into your calculator. Really quick reminder here that our confidence interval is linked to our hypothesis test. So if you're testing at an alpha level of 0.05, the corresponding confidence level for a confidence interval would be 95%. And the final concept of this chapter is, if you remember on the test for Unit 5, I gave you a specified margin of error for a confidence interval, and then you would have to find the sample size that makes that margin of error under, say, 5% or 4%. Well, what we're going to see is that T star, our new critical value for means, is dependent on sample size. So you're kind of at a loss here because you have two unknowns if you're solving for sample size. So because T star depends on sample size, what you want to do is replace it with the corresponding Z star value. This will make it so that it's not totally accurate, but it's the best thing we can do. You can't solve this type of problem if you have two unknowns. So instead of using T star, we use Z star, and then from there we can solve for our sample size.